Rudewright Academy. Learn it, teach it, remember it, binary trees. By the end of this, you will not see a static drawing. You will see one shape repeated all the way down. Start with a single box holding a number. It can hang two smaller boxes below it, a left one and a right one. Here is the move that makes everything click. Each of those boxes obeys the very same rule and can hang its own two smaller boxes. Zoom into any child and you are looking at another tree, just a smaller one. Every node is the root of its own little tree. Let me give you some plain names for the parts. The box at the very top is the root and nobody hangs above it. A parent hangs children, and the line between them is an edge. A box that hangs nothing is a leaf, the bottom of the tree. Binary just means two, so every node has at most two children. And one gentle warning, a tree grows downward, with the root on top and the leaves at the bottom. Here is the one tree we will trace everything on, so keep it in front of you. The root holds 4. Its two children are 2 and 6. Under 2 sit 1 and 3, and under 6 sit 5 and 7. The 4 boxes along the bottom hang nothing, so they are the leaves. Notice that everything to the left of a node is smaller, and everything to the right is bigger. Hold that thought because we cash it in at the very end. Before we walk it, we need 2 quick measurements. The depth of a node is how far it sits from the root, counting the edges down to it. The root is 0, its children are 1, and the leaves are 2. Every row at the same depth is called a level. The height of the tree is the depth of its deepest node, which here is 2. A lonely root all by itself has height 0. So depth belongs to a node, and height is the maximum depth. So why does height matter so much? Nearly everything you do to a balanced tree, one whose sides stay even, costs work proportional to its height. And a balanced height is about the logarithm of the size, so when you double the boxes, the height grows by only 1. But build it badly and it collapses into a single file line. That is the villain we will meet again, where the height grows with the whole count. Now let us talk about walking the tree, visiting every node exactly once. Stand on any node and you have exactly 3 pieces of work. You handle the node itself. You handle its left subtree. You handle its right subtree. And those last 2 are the same task again on a smaller tree. The only choice you have is the order, and the order gives the walk its name. First comes pre-order, where self goes first. At every node you visit it before its children, then go left, then right. Watch the token visit each node the moment it arrives, then dive deeper. When it reaches a leaf, it climbs back up and tries the next branch. Read the order off: 4, 2, 1, 3, 6, 5, 7. The signature is simple. The root came out first. Pre-order is how you copy or save a tree, writing a node before its children. Now in order, where self sits in the middle, you go left, then the node, then right. The token dives all the way left before it visits anything. Then it climbs, visits, and turns into the right side. Read it off. 1, 2, 3, 4, 5, 6, 7. It comes out perfectly sorted, which is the thought I asked you to hold. In order of a search tree spills its values out sorted for free, and that is why it is the most famous of the 3. Now post order, where self comes last. You go left, then right, then the node. A node may not be visited until both of its subtrees are completely done. So the token reaches deep, finishes the children, and only then visits the parent. The order is 1, 3, 2, 5, 7, 6, 4. This time the root came out last. Post order is for whenever a node depends on its children, like summing, measuring height, or deleting bottom up. Now step back and really see it. The 3 walks are the very same walk, with the token following the same path down and back up every time. The only difference is the moment you visit each node, before its children, between them, or after. Self, left, right, left, self, right, self. 3 positions for one little word. Visit. That is the whole story of depth-first traversal. And here is why recursion fits like a glove. The first line is the base case, an empty tree with nothing to do. Forget it, and the recursion never stops. Then you visit the node. Then you call yourself on the left subtree and on the right the same procedure on a smaller tree. That climb back up you kept seeing is the call stack, remembering where to return. And to get in order or post order, you just move one line. The structure is recursive, so the code is recursive, and the code stays short. The 3 walks we just saw all dive downward. But sometimes you want to read the tree the way your eyes do, one row at a time. Recursion cannot do that, because recursion dives and we want to sweep across. So we reach for a queue, a simple waiting line that is first in, first out. Put the root in, then take the front, visit it, and add its children to the back. 4 adds 2 and 6, 2 adds 1 and 3, and 6 adds 5 and 7. The nodes come off front to back, giving 4, 2, 6, 1, 3, 5, 7. A whole level empties before the next one begins. So how much work is a traversal, really? Do not guess it, let us count it. In every walk, each node is dealt with exactly once, visited once, and its links followed once. So the total work tracks the number of nodes. Double the boxes and you double the work. And that is the best you could ever hope for. You simply must touch every node to visit them all. Memory is the subtler number, and it splits by the kind of walk. A depth-first walk holds 1 frame per node on the current path down, so its memory tracks the height. A breadth-first walk holds 1 entry per node on the current level, so its memory tracks the widest level. For a full tree, that widest level is about half of all the nodes. Same time but different space, so a wide bushy tree favors depth first. A deep skinny one favors breadth first. That is exactly the read an interviewer wants from you. A handful of mistakes account for most broken tree code. 1. Forgetting the base case, so the recursion runs off the bottom and crashes. 2. Confusing depth with height when they are counted from opposite ends. 3. Mixing up the 4 orders, so anchor each one to its single signature. 4. Reaching for recursion when what you really need is a queue. And 5. The degenerate tree where sorted input collapses to a chain and the stack overflows. The deepest skill is spotting a tree problem out in the wild. A file system is a folder holding folders and files. An org chart is a manager with reports. An arithmetic expression is a plus with a left and a right side. A game is a position with its possible moves. Anything where one thing owns smaller things of the same kind is a tree in disguise. An answer built from the parts wants post order. The whole structure in some order wants pre, in, or post, and closest first wants level order. You master trees by tracing them on paper until the walks become reflex. Draw a small tree from scratch. Walk it all 4 ways. Pre-order starts at the root, in order comes out sorted, and post order ends at the root. Write the 3-line recursion from memory. Trace the queue explicitly, box by box. Then take real problems like height, sum, balance, copy, and find, and say which traversal each one wants before you write a single line. So here is the one model to keep. A binary tree is a node holding a value plus 2 smaller binary trees, so the shape contains itself. Almost everything you do is the same move at every node in the order you choose. Pre, in, or post on the call stack, or level by level with a queue. See the node, see its 2 smaller trees, and do the one move. Want to keep learning? Come find us at academy.rudewrite.com.